All right, folks. Today we're going to continue along in our functions unit and talk specifically of the difference between linear and nonlinear functions. Function by definition from a previous lesson is a specific relationship in math between two changing quantities where every single input produces exactly one output. Every x produces exactly one y, and there's some predictability behind functions. While a function is a relationship in math, we have learned that not all relationships are actual functions. And today we're just going to explore what it means for a function to be considered linear and what it means for a function to be nonlinear. So let's just jump right into it. Linear functions are specific. It's a function that represents a straight line graph or something that does not have a curve to it. And all linear functions can be shown in this form. F of x equals mx plus b. And today we're going to talk a little bit about what the m represents and then also what the b represents. But if you see an equation or a function in this form, you know that it will be linear. So some examples of linear functions might be 2x plus 4. Okay, it follows that form, therefore it is a linear function. I didn't calibrate my smartboard, so pause with me here because this is going to drive me absolutely insane. So jot down that note. Not the most professional setup we got going on here, but it works. All right, that should be much better and won't drive me nuts. Okay, most of the standards that we have in 8th grade lie in linear functions. This is kind of our most common. And we're going to start with something with some context so it can kind of help us understand what those m and b values represent. So the situation we have here is Kevin Malone, who's one of my favorite characters from The Office, is an accountant for a Pennsylvania company called Dunder Mifflin. Some of you guys maybe have heard of this company. He loves M&Ms and usually buys a jar and puts 500 into the jar initially. On average, he eats about 60 M&Ms per hour. Now, one of the most popular ways that we show functions are using tables, graphs, and equations. So we're going to try and show that. First thing we have to understand is what the what the left-hand side of our table is going to be, or what our independent variable would be, and then what is being measured or what is changing as a result of that change in the independent. So let's start there. Our independent variable in this case, I want you guys all think about what you might think it would be. All right, our independent or x value. In this situation, since it says per hour, that's going to be our independent. So we're just going to call this h. Okay. Now the function is representing the function in terms of h. So we'll call this f of h. And that's dependent. And what we're trying to measure is how many M&Ms are in the jar. So after 0 hours of measuring, or initially, Kevin has 500 M&Ms. Okay? And then you can see that since he's eating 60 M&Ms per hour, every hour that we go past, we know that they go down by a factor of 60. So that would be 440. After 2 hours, we've got 60 less than 440, that's 380 M&Ms. And we won't fill the whole thing in. 3 hours, we've got 320, and so on. After 4 hours, there are 260. Okay. So this is just the table part of our linear function, and it's just one way to represent functions. The second way that we represent a function is to take that data that we have available to us and put it into a graph, right? And this will be a linear graph, it'll be a line graph. So I can look here and I've got my hours on the left-hand side, my M&Ms on the right-hand side, and all I do is match them up just like an XY, right? So I'm going to label here first. Let's say that this is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours down here, and I just find those locations. So 0, 500, remember the left hand is going left and right hand is going up and down. So 0, 500 is right up here. 1, 440 would be about right there. 2 and 380 is about right there, and so on. 3 and 320. 4 and 260, and 5 and 200. Now, if this function is linear, you're going to see the lines all, or the dots all line up in a straight line fashion. And part of that linear change is that it is consistent change. That's something you should write down. Consistent rate of change. Right? Kevin is eating exactly 60 M&Ms per hour. It's not like 60 the first hour and then 70 the second hour and 30 the third hour. It's consistent. Every hour is 60. Okay? And if that's true, you're going to see this line form. Okay? You guys can pause the video if you need to catch any of that, but I'm going to keep moving. The last way that we kind of show a function is with an equation, and I think to do that, it's helpful to write it out, like exactly what's happening. So you see that he starts with 500. And then he eats, on average, 60 per hour. Okay? Now, as I showed you before, all equations that are considered linear can be shown in this way, mx plus b. All right? We have to understand what m and b is. M traditionally represents that rate. So in our situation, the speed that he is eating. So in my equation, I'm going to have negative 60x because he is losing 60 M&Ms per hour. And B traditionally represents kind of a starting or initial amount. So initial. So with my equation, I'd have negative 60x plus what I started with, which is 500. Those could be flipped around too. But that would be my equation. Okay. It's in function notation, which you guys kind of learned about last week. And it does represent this particular function. Now, linear functions are great. Some functions are not linear. Okay, here's another office reference. So Stanley Hudson gets stressed out by Michael Scott in season 5 of The Office. He has to rate his stress levels on a 1 through 10 scale each hour. And these are his results. Graph them and determine if this is linear or nonlinear change. Kind of sad, by the way, The Office got taken off Netflix, and that all of these Office references might mean more to people that have actually seen it. But anyway, we're going to show, we'll just call this generic X in this situation, the stress level as a relation of time. Okay, so we're measuring our stress over time. So when you look at the graph of this one, and you can look at our numbers and see that the numbers are not going up or down in a consistent manner, therefore this function will not necessarily be linear. We're measuring stress over here and hours over here. So let's just show that. 0 and 1. Okay, 0 hours, stress level at a 1. Okay, I didn't label any of these. I should do that. 6, 8, and 10. I'll use red so it pops out a little bit more. 1, and he's at a 2. 2 hours past, he's at a 4. 3 hours past, he's at a 9, which is somewhere up here. 4 hours past, he's also at a 9. 5 hours past, he's at a 7. And then 6 hours past, he's at a 5. 7 hours past, he's at a 1. And 8 hours past, he's also at a 1. Notice how he can never be more than one level of stress, and that's also going back to our definition of a function. So when you graph this thing out, you can kind of see that it's not exactly linear. This is called a nonlinear function because the change is inconsistent. Okay, he's not going up or down at the same rate. And we can't necessarily write an equation of this particular nonlinear function. You can write the equation for some. All right, so biggest thing is linear functions show consistent change. Since Kevin ate exactly 60 M&Ms per hour, the graph formed a straight line. Nonlinear relationships show inconsistent rate of change like Stanley's mood. Okay. All right, let's look at this particular pattern here. We're going to try and show how this could represent some change that is considered linear, and then we'll practice writing an equation of it and graphing it second. So you look at the one triangle, and what we're going to try and show is perimeter in relation to triangles. So the perimeter of the figure in relation to how many triangles there are. Now, based on that relationship, my triangles would be independent, so we're going to call that x. My perimeter is dependent, so we're going to call that f of x. Now, with one triangle, two triangles, three triangles, four triangles, five triangles, I want you guys to all in your heads right now, just count out the perimeter, and then we'll practice writing the equation. So with one, I see the perimeter being 3. With two, we've got 1, 2, 3, 4. With three triangles, we've got 1, 2, 3, 4, 5. Four triangles, looks like it would be 6. And you can kind of make a prediction that 5 triangles would be 7. All right. So now let's describe this change. It seems as if each triangle increases the perimeter by 1. And if you guys remember, all equations can be written in this form, mx plus b. All right, mx plus b. The m in this situation is just going to be 1 perimeter increase per one triangle, or just 1. So we'll call this 1x. All right. Now the b value is a little bit trickier, but it's actually not all that hard. It's essentially to say, if you take your x value times 1, what do you have to do to get to your f of x value? So let's just examine this one. 1 times 1 gets me 1, and then I have to add 2 to that to get to 3. 2 times 1 gets me 2. I've got to add 2 to that to get to 4. 3 times 1 gets me 3 times, or add 2 to that to get to 5. So 1x plus 2 would be my equation. All right, another little helpful hint. If you guys all imagine, and this is going to be kind of scrunched in here, but the value of f of x when x is 0, that value right there will be your plus b. That's a little pro trick. Since that value in this situation would be 2, that's going to be your plus b. All right. Let me jump to the equation. The last portion of this is to just graph our results. So we've got x being 1, y being, or f of x being 3. So let's just show that down here. 1. I'm going to do this just for ease. Let's see, we'll make our numbers go up by 2 up here too. 2, 4, 6, 8, 10. So now let's just match them up. 1, 3. So we go to the right, 1, up 3. There's our first dot. We should probably include 0, 2 as well. 2, and then 4 is somewhere right up here. 3, and then 5. 4 and 6, and finally 5 and 7. And you guys can again see that since that change is consistent, right, it's going up by 1 each time that we got a linear straight line function. All right, question 2, determine if the table represents a linear function, and if it does, write an equation to represent that relationship. All right, now biggest thing again is linear functions have consistent rate of change, so we have to determine that based on what we're given. Now when we look at A, I can see a bunch of different increments in x, right? We got -4 to -2 is going up by 2, -2 to -1 is going up by 1, -1 to 1 is going up by 2. So the question really remains, is this consistent change? Is the y change increasing or decreasing at a consistent value in relation with x? So let's just check here. From -2 to -10 is a decrease of 8 units. And that is per an increase of 2 units. So down 8 for every 2. And that reduces to the number -4. Okay? Now let's check from -2 to -1. This is a decrease of 4 per 1. So you guys can see that even though the numbers are changing differently, it still does appear that y is decreasing by 4 per 1x. But let's just make sure here. The final one that I'm going to test is from -14 to -22. That's a decrease of 8 units, and that is per increase of 2 units. So again, we've got -8 per 2, which reduces to -4, -4 per 1, and then -8 per 2 again, which again simplifies to -4. All right, so this is for sure linear, okay, because of that constant change. Now the second part of that is to represent the table with an equation. Well, I've just found that rate, decrease of 4 per 1x. So in terms of my equation, f of x is equal to -4x plus b. We don't exactly know what the plus b is yet. Here's one way to get that plus b, is to take any of these different xy combinations. So I'm going to just choose a positive one. I'm going to choose this 1 and -22 and then plug it into my equation. -22 being the f of x, or the y, is equal to -4 times 1 plus b. And all I have to do from there is just kind of do math. -4 times 1 is -4, plus what number would equal -22? Well, now we got an equation. My b value is going to be -18. So my total equation is taking that rate, which is -4 per 1, and then the b value, which is -18, and throwing them into the equation, -4x plus 18. Look at that second one here. Separate my work a little bit. 1 to 4, that's an increase of 3. 4 to 7, that's an increase of 3. 7 to 13, that's an increase of 6. But notice how that's 6 per 2. The other ones were per 1. Okay. So whether it's 6 per 2 or 3 per 1, that all reduces down to an increase of 3 for every 1x. So that's our m value. Now, as I said before, if you ever can identify the value of y when x is 0, that's going to be your b value. This one, it's actually given to us. Our b value is going to be 1, so it makes the equation quite a bit easier. 3x plus 1. And notice how that works for each one of these. 3 times this x value of 4 is 12. 12 plus 1 gets you 13. 3 times this x value of 5 gets you 15. 15 plus 1 gets you 16. All right. I think we'll call that lesson 1. We're going to make a second video for lesson 2.